Welcome to another concept session. I've been gone for a while and I want to restart with a new chapter. Today we're going to talk about Newton's laws of motion. So before I forget, don't forget to subscribe to this channel. When I update, when I post something, you can get some kind of reminder, a notification. You can check out my website here, where this is the textbook I wrote, and you can tell your friends and spread the word about this channel. I hope more people can really learn the basics of physics from this channel. Okay, so my approach is try to give you a more or less correct explanation of things, although at different level physics has a little bit a more deeper explanation and a little bit more correct. So we are right now just looking at some intermediate level, beginning to intermediate level. So okay, let's look at these things, these concepts which call Newton's laws of motion. They are basically laws which come from observations were made, and those laws Newton put them in a more mathematically relatively sound footing. Okay, so there are, you already probably know there are three laws of motion. One is called law of inertia, another is called second law of motion, and another is called third law of motion. So traditionally you see those three laws, but there's just basically one law, and the other two laws are consequences of that one law. So traditionally you have maybe memorized one is called inertia, and this is just a word, and I don't think that anybody knows what it really means. The second one goes by F equals ma, and the third one is equal but opposite. Equal but opposite. The force on one but the other is equal and opposite. So it's about two bodies. So this one is about one body of mass m, and this is about also one body, and this is about two bodies. So you can see, if I know one body, I should be able to get what will happen when we have two bodies. So this is the main law, and you have to understand that law when that is true, how to make use of it. Then you can actually say, okay, when is these guys turn out to be consequence of that. All right, let's see. You probably know that the acceleration will depend on, when you look at this, you can see the acceleration is depend on what kind of frame you're in. So for instance, suppose there is a car and the truck which is moving in that way, and its acceleration is in that direction with magnitude, say 5 centimeter per second square. What do you mean? What you mean is there is this frame, or that this is fixed, and with respect to this guy's acceleration, this is the acceleration with respect to this frame. Now imagine there was another another truck over here, and this was also have acceleration in the same direction, 5 meters per second square. And we look at that truck from, this is fixed to, so this is A and this is B, fixed to B. And so when you look at that with that truck with respect to this, you will see the acceleration of A with respect to B will be 0. So another way to say it is, another way you can imagine is there is a person here inside the truck and maybe another frame over there. So this is person C. So with respect to C, what's the truck's acceleration? 0. So you can see the acceleration depends on which frame we are referring the acceleration value to, right? So this law here, but the force is independent of frame. Force on this mass M, on M, independent of frame. So this side depends on frame, this side doesn't depend on frame, this is independent of frame. So you can say this entire equation must depend on frame. Okay, that means the equation F equals ma, when you write that down, depends on frame. And so how can this be a law? How can be like such a universal fact that depends on how I look at it, right? So you have to say what kind of frame that this law really applies. So these are very special type of frames, and they are defined by this equation itself. So there are the claim by Newton, and before that is kind of Galileo. The claim is that if you look at from the perspective of this special set of frames, it's not just one frame. There are infinitely many frames like that, but these types of frames are defined so that this equation is correct. So we call this frame, so there exist frames of reference in which this law is correct. F force, net force, so this is so net force on this particle P, so equals mass times acceleration of M in that frame. This is valid for every particle of mass M. So there exist these frames, okay, in which this is true, and we will call these frames, we'll give it a name. We'll give these names called inertial frames. Okay, so this is the second law, that there are these special frames in which this is true. So one of the characteristics of these frames is, how do I find these frames? Well, let's look at what the consequences this will be in this frame first to find these frames. One of the consequences will be, if there are no force, then there will be no acceleration. So one of the consequences, if no force on m, this particle, then m does not have acceleration. Acceleration of m is 0. Is 0. So if acceleration is 0, then its velocity cannot change. So that means its velocity cannot change. It's not saying velocity will be 0. Very important to note that not saying velocity will be 0. Will have to be 0. So it's only saying acceleration has to be 0. Okay, velocity will be constant, and each 0 is just one set constant. Okay, velocity constant will be 0 because you know the acceleration is equals to dv dt. So if this is 0, then this has to be constant. Now this is law number 1. It says no force, then the object's velocity cannot change. Velocity has to remain constant. So it's not telling you what's behind the constant velocity. If something is going at 5 meters per second, it's not saying what made it go 5 meters per second. It's saying this velocity cannot change. It's not saying what's the source of that velocity, why it cannot change. It's just saying there is no force, means no change in velocity can occur. Change in velocity has to be connected with some force that's present at that moment. Okay, so the way it's made even mysterious is says there is a natural tendency of objects to move at constant velocity, and that natural tendency is called tendency of inertia. It's called inertia. There's every object, every particle has a innate tendency. So it becomes very what is that innate tendency? Well, no one can really point to a source of innate tendency. So I don't really like to mystify those things. You just look at this and it's automatically the consequence of these kinds of frames. So there in these frames where this law is applicable, we will find that if there are no force, then no acceleration. So this says valid in these special frames, or inertial frames. Okay, let me erase this so I can write. Okay, so in short, we have some frames. We haven't said how we're going to find it, but in those frames, acceleration of an object will be 0, meaning object will move at constant velocity, will move or stay at rest, move at constant velocity or stay at rest if force on m is 0. So you really don't need this consequence of that, except that we can use this to look for frames. So we can as we look around, broaden the more and more universe, you can see that. So this is our universe. So one such frame will be assuming the center of the universe is at absolute rest. Okay, so this is at whatever that may be. This is something very questionable. Nobody knows, right? At absolute rest. This is the center of the universe, absolute rest. So we have a preferred frame here. We can say here is some particle P, and maybe the other particle, but on this particle there's no net force, so this particle will have a constant v with respect to this frame, or with respect to this frame. So now we're not going to be able to go to the center of the universe and get this frame, so we say, okay, we have some, let's see, there's a galaxy or a star here, or say Earth. Suppose we assume the Earth's or sun, so maybe this is sun. You can say maybe sun is moving at constant velocity with respect to this guy. Then if I were to put a frame on the sun, you will find that with respect to sun, velocity of this will be with respect to sun, that will be also constant, because this is constant and this is 0. So you can say from the relative velocity point of view, so from here to here and here to here, so let's call this r vector, and let's call this r vector. So let's call this rs vector. So rs vector equals to r vector plus r vector, or minus r vector. This plus this equals that. So if I take a time derivative, drs, so this is with respect to sun, it will be dr dt minus dr dt. Now this is the velocity of sun, which is constant. This is the velocity with respect to the center of this universe. This is also constant. So v with respect to sun equals to v of this particle p, okay, of particle p, of p, and v of p with respect to this at rest minus v of the sun, we are assuming to be constant, and these are with respect to center of this, let's call it O, with respect to O. So this is constant, this is constant, so therefore that is constant. So now we say if something is moving with respect to no force, it has no force with respect to center of the universe at constant velocity, it will move with respect to sun at a constant velocity, as long as the sun has a constant velocity with respect to that. And in that order we can bring even on the earth. So if you look at a little bit, suppose I have earth. On earth, I say the earth's its motion itself is constant. It's not constant, but if you assume for the duration we do the experiment, it's constant. Then same logic can say, well, if something's, this particle p is moving with respect to earth that way and has no net force on it, so in that case it will have this property of inertial frames valid, right? See, in a sense, law 1 you can use to find inertial frames with this logic, right? But you need to find inertial frames so that you can have the second law of Newton. But the inertial frame, to find inertial frame, you have to somehow start at an absolute rest frame, and from there you can move up and find more or less inertial frame, like Earth's frame. You know, Earth is rotating, so a point on Earth, if you attach a frame, it's going to rotate, and so its velocity will change with respect to the absolute space. However, if you're not doing experiment long enough, then the change is not long enough, change is not much, and could be ignored for the purpose of that particular experiment. And then you can apply this to that experiment. However, the law will be violated because you're not in inertial frame. So it's only true, supposed to be true only inertial frames. Okay. So that's we can talk a little bit about what happens when you don't have a non-inertial frame in just a minute. Okay. So before we do that, let's just finish up the discussion of law number 3. So this is for one body, right? Law for mass m, and this also for one body. So when you build up a complicated object, you can have, say, the next complication will be two bodies. So let's see, you have mass m1, m2, okay? And for the sake of discussion, let's see it is connected by a rigid rod of mass 0. We have just two bodies. And we want to study the motion of this, okay? So in a maybe there's a force on m1 by m2, so there well, let's not complicate. Okay, let's not complicate, just let's get rid of that. So just have these two bodies, and so there will be a force on each one on the other. So maybe if you look at this guy, if there's a gravity, maybe this will try to pull F by 2, and if you look at this, there will be F by 1. So F by 2, and this is 1 and this is 2, right? So this is the force on that guy, this is the force on that guy. Now if I look at that as one system, then you can say then what will happen? That's the question I'm going to ask. Okay, so let's write down law for this and law for that and see what we come up with. So suppose we're looking in an inertial frame. So we're looking at inertial frame. So this F on 1 by 2, so that's this force, equals to mass of 1, acceleration of 1. And for this guy, the law will be F on 2 by 1 equals mass of 2, acceleration of 2. Let's add these up, okay? So if I look at them together, let's see what happens when I add this guy. So this side is the sum of the two forces. F on 1 by 2 plus F on 2 by 1 is m1 a of 1 plus m2 a of 2. Drop the offs, okay? And let's see if we can do a little bit with it. We can say, want to look at both of them together, then the mass will be m1 plus m2. So we can kind of multiply and divide by that, m1 plus m2. So m1 a1 plus m2 a2. This quantity is a unit of acceleration. There's some type of acceleration, and this is the total mass. So if I'm looking for this, this one, you can see corresponding quantity of, we can say, mass weighted velocity. This mass weighted acceleration So we may call it mass weighted acceleration. So some kind of acceleration where each one of the mass multiplies its acceleration. And we can say mass weighted velocity, so m1 v1 plus m2 v2 over m1 plus m2. So this would be mass weighted velocity. It is a unit of velocity, but I don't know, just a mathematical thing. It's not the velocity of any object. There are only two objects, not of m1 or m2. It's not a velocity of two together or something like that. It's just mass weighted. And if you carry one further and look at the positions of the two, so there will be the position R1 and the position, this guy will be R2. So let's look at this quantity, R1 plus M2 R2 plus M1 plus M2. So this is mass weighted position. So this is mass weighted position. So you can see if M1 is larger, then this will be closer to it will be some point connecting between them. So it will be like somewhere here. So this we can call this, say, R. So this will be R vector. So we're looking at that point, motion of that point. So this is the velocity of that point, say, let's call it big X. And let's just see, point C, usually called center of mass. We call it center of mass, and so this will be like a velocity of that point in space, velocity of center of mass. So this is center of mass, and so this, if you take a time derivative, this is the acceleration of this point in space, which is associated with these two masses. So these are mathematical things. So it's like acceleration. If these objects were fixed distance apart, if they were fixed distance apart, then if R1 and R2, the difference between, they were separated. That's why I was drawing a line here. If I kept this fixed distance apart, then the point will be a fixed distance from one or fixed distance from two. Okay, so if you look at this way, then for this combined system, if acceleration is zero, if this is zero, then the forces have to be add up to zero. So if acceleration is zero, the force has to be zero, just from the law 1 itself, right? So if there are no external forces, so no external forces means these internal forces have to say no external forces. What does it mean? Will mean there are no other objects around. Will mean no ACM, no acceleration of A1 or A2, so no acceleration of ACM, right? So there's no A1, no A2, so no outside forces. Then this combination of the acceleration will be zero, no ACM. That will mean when I add these two guys, should be zero, no net force. That means F on 1 by 2 must equal to minus F on 2 by 1. Now this is the third law. This is the third law of motion. Notice, very important, that they're not equal because there's a negative sign here. That's why in the opposite direction. So this force on this by that is in the opposite direction, the force on this by that. Now I drew here the force were in the line joining them. There's no requirement. It's just saying the force, there's no restriction on the direction of these forces, except they're opposite to each other. Which way they point in space, they're not. So one would be like if this is 1 and this is 2, maybe F on 1 is that way by 2. Then all it's saying is if it's that way, then force on 2 should be that way, exactly same size, F on 2 by 1, so that they're opposite in direction. They don't have to be facing each other in the space. It's just that when you add them up, you should get a 0. That's the third law. Okay. Okay, so although so this is the third law. Although we did this little derivation where we use inertial frame to come up with this law, but since forces are independent of frames, this should be true in every frame. So that's the extension. I'm going to make it, we're extending it. These are in inertial frame, this is inertial frame, but this one, although we did this little derivation, but that derivation was limited, and it kind of removed, in that derivation, removes all the frame dependent ideas, and what we obtained were relationship between things which are frame independent. So this is true in every frame. So in a sense you might say that this law is an independent law, and actually this law is connected with what is called whether later on we're going to talk about the conservation of momentum. So if you go a little bit deeper, you find that this has to be the case because momentum has to be conserved, and I don't have time to get into that today. I just wanted to point that out, that in the future we are going to take it on in another context called conservation of momentum. Okay, so those are conceptual things about Newton's laws of motion. The very last thing about conceptual thing I want to talk about is this equation. This equation is true moment by moment. So it's actually at each instant in time that's the case. So we always, when we're talking about problems, we have to look at what's happening to M, my system, at a particular instant. So this is very important to keep in mind. So this F on M is a function of time t. So at that instant equals to mass A of M at that instant. So that's, we pick an instant, we draw the forces, we try to find the vector sum of the forces, and then find the find an equation like that. Okay, so let's do one simple example. All right. Okay, so let's look at this standard example. So here is you can consider this to be a particle of mass m. So we just think of this as a particle. It's a block, but we think of a particle, so that we can assign this a coordinate x. So let's see, so inertial frame, so we can think this as an inertial frame. So this is attached to some table, so this is attached to some wall, and this is some table, and of course this table is on earth, which is moving in the space with respect to the fixed frame, and we are going to say that this is equal to 0 with respect to this guy. So this guy's v is equal to 0 with respect to this guy. So this is the absolute frame, absolute rest frame, and so this is v equal to 0. So if I use a frame I will use a frame like this. So this is O, so this is inertial frame. Okay, so this is at some time t. Okay, the spring's length at this time, of course, changing some length times t. And we'll say spring's length, spring does not apply any force if it has a spring is when you pull it, it tends to pull from both ends, but the spring doesn't apply a force when it's at a original length, right? Undeformed length. So let's L0 equals to unstretched length of spring. So the force that spring will apply, this is the only force, and then there's a force from the table. So there are two forces from the table in this case. So there's a it's called normal force from table. So table is trying to push the block up, and the gravity is trying to pull the gravity on M. So this is gravity on M is trying to pull this, and then another force is the force from the spring. So if this is L0, so right now it's stretched, so the force will be that way. And let's call this x-axis, and let's call this y-axis. So when you look at F on M equals to mass times A of M. So this is a vector equation, and so you can have an x component, y and z components. So let's look at the x component of these things. So x of these guys, this does not have any x, and this does not have any x. So this is the spring is the only x. So the spring force, its x will be, now it's pointing to the negative directions, and how much it is some kind of spring constant. So from here to here is x, so this is all the way to x, but the force is only from the stretched part, so x minus L0, and y force is just Fn minus gravity, so that's just equal to Fn minus F gravity, let's call it G, F gravity. You learn that this is actually mass times G, and this I don't know, there's nobody knows how much you. So those about the forces. So that's the left side. On the right side, mass times acceleration is d square x dt square for x acceleration, and for y acceleration d square y dt square. Now, because the constraint, we have y equals to 0 because on the table y equals to 0 always. That just means d square dt square equal to 0 also. So now in that equation, let me erase a little bit. So second law tells me two equations. Along x I have minus k x minus L0 equal to m d square x dt square, And the second equation is along the y-axis is Fn normal force from the table minus mg equal to 0. But this is 0. So this is 0. So these are two equations, and then of course you have to solve them. These are now math equations, they have to be solved. So initially what we're going to do is not have this complicated. Over here you can see that this side is a function of time, and this side is a function of time. So you pretty complicated. You have a derivative and this function of time like that, and the solution of this thing is a little bit difficult. We're going to come to it in the future. These are called simple harmonic motions. As you know, it's going to go back and forth, so it's going to be periodic motion. It's going to be able, we will be able to write it in terms of sines and cosines, or exponential with imaginary in there, right? So we'll be able to write that in sines and cosines in the future. For some time now, what we're going to do is this left side will turn out to be constant in time, and so it will be easier to solve this equation. So acceleration will turn out to be constant most of the time in our studies for some time, okay, just for the simplicity. But this actually, to keep in mind that this type of equation is always, this side is on particular time and this side is on particular time, and this may become a complicated equation, and some may not be solvable by simple means. Okay, so I'm going to stop here. This was a concept clearing episode. I know a lot of you had some Newton's laws exposure, but I want to be sure that you know the role of a special frame when you write Newton's law. And in the next episode, I'm going to try to address Newton's law in a non-inertial frame. Suppose I'm an accelerating frame, a frame which is accelerating at a constant acceleration, at a varying acceleration, whatever, okay? If I have a frame which is accelerating with respect to this absolute frame, absolute rest frame, then what will I do? Like suppose I am in a accelerating truck and I want to observe nature from the seat of that truck. What will be the law I should be using? It won't be F equals ma. It will have to be changed and adjusted, made appropriate adjustments made, and that is what's behind it, right? When we make more accurate observations from Earth. The Earth is rotating, so rotation of Earth is going to make some difference. But so if I can't use F equals ma, what can I use? That we're going to talk about next. All right, I'm going to stop here. Okay, bye.